Hey everyone, welcome back to class. In this lecture, we're going to be extending our work on inferential statistics from t-testing to ANOVA. I'm going to give you guys a foundation of why you need to move from t-testing to ANOVA based on having different independent variables of interest, and explain to you how to implement this test in R and then interpret the output. So the big foundation of why we need to move to ANOVA is sometimes we have grouping variables with more than two groups. As a reminder, in our t-test lecture, we focused on binary independent variables where there was a group for majors and non-majors, right? So majors were 1 and non-majors were 0, and we compared the different means for midterm scores between majors and non-majors. There were only two groups. But say we wanted to compare across multiple groups. There's a lot of different scenarios where you're going to have more than two groups. In this working example that we'll move forward with, we're going to look at all the different kind of classes, undergrad classes, freshman, sophomore, junior, senior. So maybe instead of looking at majors and non-majors, we want to look at all the different classes' performance on the major, because we might have some kind of causal mechanism we think will affect performance based on what year you are in undergrad. And this is inherently more than two groups, right? We're comparing against 4. So we cannot use a t-test when there are more than two groups. We have to move into something like ANOVA, which is an analysis of variance. So we're going to still be in this world of calculating test statistics. We'll move into talking about that a bit more concretely in the specific test statistic you need to find for ANOVA. In addition to the fact that we are only still working with non-directional hypotheses. As a reminder, our non-directional hypotheses are something that says there is going to be a relationship between X and Y, instead of something like there's an increase in X as Y increases, or a decrease, right? So we're keeping the very neutral language of there just is going to be a relationship between the concepts that we specify in our hypothesis. So as I previously stated, the levels of measurement in ANOVA, the independent variable is going to still be categorical, right? And the two different kinds of categorical are either nominal or ordinal. But we have to have more than two categories, right? So ANOVA helps us compare different groups with more than two categories. And then our dependent variable will still kind of calculate the differences in scores on the midterm. So it's going to be interval ratio as well. So remember, our IV is still categorical, either nominal or ordinal, but we have more than two categories. And then the dependent variable is still interval ratio. So it's comparing the performance on the midterm by more than two groups. So to solidify the difference between ANOVA and t-testing on when you should implement them, again, the t-test is when you have binary groups for your independent variable. For example, we're looking at Democrats and Republicans average score on something, or majors and non-majors average score on something. So there's only two different groups. As opposed to with ANOVA, we have more than two groups. For example, that we're going to kind of work with in this lecture, the different class groups, freshman, sophomore, junior, senior. So we have 4 groups in this case. We know we can't use t-tests. We have to use ANOVA. So again, we're going to get 3 different values that we can either interpret kind of by hand while looking at the table in the same way we did last time, or we can just interpret the output, our output. I'm going to show you the basics of the hand interpretation or the kind of analog interpretation. And then I'll show you what I just want you to do in terms of our class, which is doing the R kind of coding and interpretation of it. So we're going to get 3 separate values, same as last time. There's going to be a critical value that we're going to compare our test statistic to see which one's more extreme, or if it's less extreme than our critical value, in the same way we did with the t-test. We're still going to be getting our degrees of freedom, which is our understanding kind of the variability of the data set. And then we're also going to get a significance value or a p-value in the same way that we did last time. And that p-value can be interpreted in the same way that I told you guys about in the last module. So the hypothesis that we're going to work with is that there is a difference between different years in undergrad and their performance on the midterm. So our causal mechanism may be something like we could see a world where those farther into undergrad do better on their midterms because they have more experience taking midterms or taking hard tests than those who are earlier in the process. So hypothesis is going to be how different years in undergrad perform on the midterm, right? Our independent variable in this case are all the different years. So freshman, sophomore, junior, senior. And our dependent variable is performance on the midterm or the midterm score. So instead of with t-tests where you calculate a test statistic, ANOVA is going to calculate an F statistic, which is an assessment of the variability of your groups. The F statistic is the difference between the variability between groups, so between freshman, sophomore, junior, senior, and the variability within groups. So the differences in scores within freshmen as a group, the differences between scores within sophomores as a group, and so on and so forth. You again can calculate this by hand, but I'm going to show you how to get the output in R. We're going to show you how to interpret it based on a table, and then also show you how to interpret it just straight from the R code. So again, the F statistic is going to assess the differences between group variability and within group variability, and then ultimately just is going to allow us to assess if there are statistical differences between all of our different groups. So here's what the code looks like. We're going to use a one-way test. So we know it's going to be a one-way test. So there's one-way, two-way, three-way ANOVAs. Because we only have one grouping variable, class, or one independent variable of interest, it's a one-way ANOVA test. If we had multiple different groupings, it would be two-way, right? So if we had class plus, let's say, different majors, not just major and non-major, but political science, education, economics. If we had another kind of grouping variable like that, we would use a two-way test. But we can use a one-way test, and that's all we're going to cover in this particular lecture because we have one grouping variable. The function one-way test is going to use that same sort of tilde language that we use for t-tests. So again, our dependent variable is the midterm. Our independent variable is class. Our data is the student data set, and the equal variances is just an assumption that we have to kind of put in there. There are all these assumptions that go along with these inferential statistical tests that are beyond the scope of this course, but I do want you to know that you have to have variances equal to true. So something to note, we don't have a $ in any of these variable selections, and I'll tell you why. So there are certain cases where you can move away from that because of the direction that R reads. So you don't have to have $ in this case because R reads from right to left, meaning it reads student data first and then reads midterm class in these sort of functions specifically. In other cases, it doesn't read it that way. It reads left to right like we do, which is why you have to use the $. But in these sort of, a lot of these statistical functions, if you specify your data properly, you don't need to use the $, because R is reading from right to left instead of left to right. So you can copy this code as is and it will run. In this case, we get an F statistic down here at the bottom in the output of 19.828. And then we get two different degrees of freedom values, one for the group, one for the overall number of observations. The degrees of freedom for your group is just the number of groups minus 1. So we had 4 groups, minus 1 is 3. So our degrees of freedom for the groups are 3. And then the degrees of freedom for all of the observation is the number of observations minus the number of groups. And so we get 37. We also get a p-value too, but we're not going to deal with it quite yet. I'm going to show you what it would look like to look it up on the table and on a number line, and then we'll move forward from there. So again, we get a table similar to the t-test, but a little bit different because we have 2 different degrees of freedom. So this is assuming we want a p-value of 0.05. This is in the top left-hand corner of an alpha of 0.05. That's our statistical significance threshold. We're going to go and use the line on the far left-hand side of 40 because that's the closest that we have to our degrees of freedom of 37. And then we're going to go over 3 rows to row 3, or variable or column 3. Column 3 denotes the degrees of freedom for the groups. Okay. So on the columns, we have degrees of freedom from the groups. In the rows, we have degrees of freedom for all our observations. So we get a critical value of 2.8387. So that's going to be the variable or the critical value that we'll compare our test statistics to see if we're as extreme or more extreme than that test statistic. So again, remember we have a normal curve that we're going to compare our test statistic to. As a reminder, our test statistic was 2.8387. So our test statistic is going to fall over here to the right in +2, a little bit above 2. And so we also know that our critical value is 2.83. Our test statistic is 19. And so 19 is going to fall way out in the tails, right? So we know that we have a statistically significant result because 19 is way bigger than 2. Again, it would be statistically insignificant if that test statistic fell between positive 2.8 and negative 2.8, right? That's like kind of our boundaries set by this table. Okay, so the boundaries are set by this table, and the test statistic that the F statistic that we got here, which is also a test statistic, is 19.828, which we know is going to fall way out here on the right hand side of the tails. So we know that we have a statistically significant result, which means that these groups are significantly different on their performance on the midterm. So just to wrap this up again, so our F statistic is 19.828, which we know is much greater than our critical value at 2.8. We had the degrees of freedom, right, which we find here, 3 and 37. And we also have a p-value of 7.865 e to the -8, which means it's a tiny number, right? This is our exponential, our scientific notation, where because it's a -8, we would or move our decimal point to the left. So we know it's a very small value and less than 0.05. So in this case, we can say there's a statistically significant difference between the different majors and their performance on the midterm. We can't at this point say anything about what that difference is between the different groups. We'll have to move into a different statistical test, but we know that there is some evidence that these majors perform these different classes perform differently on their midterm. So we have some tentative evidence. Again, to interpret this, we have a point, because we're moving our decimal place based not only on the scientific notation that we were given, but also to make it a percent. But there is a tiny 0.00000, a lot of zeros, 786% chance that the relationship would be true if the null were true. So we can reject the null in this case. Again, that is much less than 0.05. So we do have a statistically significant result there. So I want you guys to be thinking about how this language relates to t-test. So a lot of the code looks really similar. The interpretation looks similar. But in the case of test statistic or the t-test, our test statistic is a t statistic. And then in the case of ANOVA, our test statistic is an F statistic. But we also, if we wanted to kind of analog compare them on those tables, the process would look really similar. It's just the degrees of freedom change a little bit in terms of the ANOVA because you have two different ones, right? One for the group, one for the total amount of observations. But you still are going to compare the p-values in the same way. So relative to a p-value threshold of 0.05, are we statistically significant? Since we were much less than that p-value of 0.05 in this case, we were able to reject our null hypothesis that there wasn't a relationship between year and undergrad and midterm scores. So moving forward, we're going to talk a little bit about how to talk about the group differences a bit more concretely, so we can actually find out what the differences are between groups, not just that there is a difference, but there's a certain kind of difference between groups. And you'll notice again that a lot of that code looks really similar. And I think you'll have a good framework to interpret these things moving forward.